Hello, and thank you for watching our presentation. In this talk, we're going to be discussing the tracing infrastructure of the Linux kernel. You'll see some of the legitimate uses of this infrastructure, but then we'll also spend a lot of time looking at the abuses that malware and malicious users can get out of this infrastructure. And then we'll also look at new memory forensics techniques that we developed that allow for deep inspection of the infrastructure and all of its different components. And the reason for this is memory forensics plays a vital role in modern investigations, but current techniques are essentially blind to this infrastructure. So if you have malware abusing it, then there's no direct way to get it, and in some cases you'd have to be pretty lucky to be able to find it at all if this type of malware had infected your system. And what we're seeing on this slide is a very high-level look at this tracing infrastructure and all of the parts of the operating system that are exposed to it. This is a famous picture because it comes from the eBPF documentation. It comes from Brendan Gregg's website. He's done a ton of work with eBPF and also wrote the book on it. And so if you look inside the rectangle, you can see all of these places of the kernel. You have the memory manager, the process scheduler, the entire networking stack, all the components of the file system, as well as dealing with the actual data on the disk. You can interface with the system call table and all of the functions, and then through this API, you can also inspect running applications as well as data that they're generating. And this is the high-level view. As I said, we'll see that the subsystems under the infrastructure and the ones that eBPF relies on are not just limited to these. You can hook the entire operating system, modify how the operating system works. So through this kernel infrastructure, there's really an unlimited set of power that both legitimate tools can get if they want to monitor system activity, as well as that same unlimited set of power for malware. If you've never used eBPF or you've never seen the output of the utilities or interacted with it yourself, I would definitely recommend the toolset that you're seeing described on the slide here. This is part of the Ftrace suite of tools. They're all open source. They're available on GitHub. You can also install them very easily on really any Linux distribution. But as you see, there's separate tools to examine each part of this stack. So if you want to see what it looks like to monitor certain parts of the network stack or the scheduler, system call table, whatever it might be, before you deep dive jump into the forensics aspects, I would spend some time with some of these tools to get an idea of what's really happening on the system. What you're seeing on this slide is some example output from those utilities that are a part of Ftrace. On the top left, you see OpenSnoop. This is going to tell you every process that's running, and when it accesses a file, it's going to give you the full path to that file. In the top right, you see bash readline. This is going to inspect every bash process that runs on a system and tell you all of the commands that were typed in. In the bottom left, you see exec-snoop. This is going to monitor the system call table for all of the system calls to execute processes. And then for each process, it's going to give you the name as well as all of the command line arguments. And then if you look at the bottom right, you see the entire source code to exec-snoop.bt. And what this is doing in its begin function, it's printing out the headers, and then within the function that it registers its tracepoint, which we'll talk about those more later, but in this case it's a tracepoint to monitor the system call table, and it wants to monitor any function that is part of executing a program. And then you can see in the source code for that function, it's going to print out the time the program was running, the PID, and then also all of the command line arguments like we saw on the left. To get a BPF program running, there's a few steps. One is you can either write in the Ftrace sort of wrapper language like you saw in the last slide. Obviously that's very powerful, but it doesn't expose absolutely everything. If you want to deal with eBPF at the raw level, then you're going to write in C and call the APIs and so on. Whichever route you choose, you're eventually going to need to compile that code and generate the BPF bytecode. This is what's actually sent to the kernel to run. Before the kernel allows it to run, it needs to pass through the verifier. This is going to make sure that the code does not perform any operations it shouldn't or try to read memory it shouldn't and so on. And it's only if that verifier accepts the code is it allowed to run. If code does pass the verifier, then it's going to be sent to the full BPF engine. This is going to evaluate that code, execute that code, gather whatever data it's trying to gather, and it can do a lot inside the engine itself. But then for many of the features, especially the ones we're interested in, it has to rely on other subsystems to do the work. These are subsystems that existed before eBPF was a thing or before it became so popular, and they provide capabilities for hooking kernel functions and other specific things. And so again, BPF doesn't want to reinvent the wheel, and it just relies on them. What this means for us as forensics analysts is it's not just enough to examine the BPF subsystem itself, but we also need to have memory forensics techniques that can examine all the other subsystems as well. So the K-probes, the Tracepoints, and so on. That way we can get a complete picture of what was going on at the system. That way we can get a complete picture of what was going on the system, and we can make sure that we're doing thorough investigations. Because of how powerful eBPF is and the capabilities that it gives to system administrators and developers and just anyone who wants to monitor a system or troubleshoot a system, it sees wide use in production. This is especially true of companies that heavily work in the cloud, obviously heavily work with Linux systems. And there's also a lot of really cool public documentation and talks that these companies have given that explain what they're doing with eBPF. So if you want to learn more about eBPF, see how it really looks in production, I would highly recommend following the resources at this link. For Netflix, Google, and Facebook, I've linked to some of their most thorough and in-depth documentation that they have for how they use eBPF. And then I would also highly recommend checking out the talks from the eBPF Summit last year. All these other companies spoke there. The talks are not long, they're like 5 to 15 minutes each, but you have their actual engineers speaking, talking about how they use it in production and the value they get from it. And so again, these resources are very nice if you want to see what eBPF allows enterprises to do, large companies to do, and how you might encounter it being used in your investigations. Before we wanted to really deep dive this infrastructure though, we first wanted to see how prevalent it was across normal distributions. We knew that big companies were relying on it. It was very popular in, as I mentioned, kind of tech heavy spaces where there's developers or cloud specific companies. But we wanted to see if you just spun up a cloud instance or if you just installed regular Linux distributions in your corporate environment, what were the odds of you having these subsystems enabled, that fact that eBPF code could run right away or kernel modules could call into these subsystems on their own. How many of those default kernels had this information just available and the subsystems available without any modifications? So to do this, we relied on the database of kernels that engineers at Velocity maintain. These kernels go back years and years for every major distribution. And it's not just a big folder where all the kernels are downloaded. All of the metadata is pulled from these kernels and put into a database. There's then a really nice API built around querying out these specific metadata. And so what we wanted to use was the configuration options, because as we'll talk about on the next slide, to figure out if these subsystems and all of this tracing infrastructure is enabled on a specific kernel, you have to know what its configuration options are. And at the time of generating these statistics, the database held about 15,000 kernels. So to start, we consulted the BPF trace documentation. This lists specifically which kernel configuration options you need for the features to be present. And it also says that the kernel version has to be at least 4.9. So the first thing we did was filter to just the kernels that were at least 4.9 in our set. This put us at around 5,400 kernels. We then wrote a script that queried the API to figure out which kernels had all of the options present. And initially we saw that about 83% of the kernels had all of the tracing features enabled, but the results were really confusing because they were across distros, and they seemed, the kernels that didn't have all the features were across distros, and it seemed very focused on 4.9 and 4.10 kernels. So we looked at which options were actually missing from these kernels, the ones that were needed, and we saw that for basically all of them, it was the same two options. We then consulted Google a bit and saw that those options weren't actually added until about 4.11. So that makes sense. Those options can't be there in 4.9 and 4.10. So we updated our statistics script with that workaround, and then essentially all kernels except for the ones that were this Ubuntu KVM variant that you wouldn't see in production anyway, all the other kernels had all the options needed for the tracing and for eBPF. And so what this showed is that essentially any kernel that you're going to encounter during your investigations will have these features present, which means they can be abused by malware. So what we're going to do now is walk you through all of these subsystems. We're going to explain them briefly, show you some code that we use from our proof of concept. For each proof of concept, we infected a virtual machine with it, so that would give us a memory sample, and then we show on the following slide the output of the plugin that we wrote to detect this behavior. If you want all the details, all the kernel internals, as much technical detail as we could possibly explain, all of that is in our technical paper that accompanied our talk, so please read that and then obviously let us know if you have any questions. For the first subsystem we looked at, it was Ftrace. This is used for tracing functions as well as events. You can see with our proof of concept, we configured it to hook the sysclone and the sysexecv system calls, and then the proof of concept is going to set filters on the addresses of where those functions starts, and then it's going to register the Ftrace handlers for them. You can see here, this is the output of our new Linux Ftrace plugin, and it correctly identifies that there are traces for the execve and the clone system calls, and then the plugin also correctly identifies where those traces are pointing to, or what's the hooking code. That is the Ftrace hook kernel module, so that's our proof of concept, and then all of the hooks go through the thunk function, which then redirects them out to the appropriate handler. So again, before this plugin, there was no way to directly detect this through memory forensics, but now by just running the plugin, you can very easily see if any malware is abusing this feature. After that, we then looked at the Tracepoint subsystem. This also allows for hooking functions in the kernel. The only limitation is that you can only use this to hook functions that define trace points at compile time, but in practice that's not too much of a limitation. All the functions that seemed interesting and that malware would hook seem to have trace points. On our test systems, all of them had at least 1,000 trace points defined. So again, it has to be a compile time thing, but in practice it's not a huge limitation. You can find trace points for the functions that you actually want to hook and that are actually of interest to you. For our proof of concept, we configured it to hook the page free and page alloc functions. Our callback functions for those, so those are the ones that will get called every time the hook is activated. That was probe page free and then probe page alloc. The way the proof of concept works is it uses the for each kernel tracepoint function that's going to call whichever callback you register for each tracepoint and allow you to find the actual address. So the proof of concept will do that for whichever functions you ask it to in the interests array. And then once it's found the actual tracepoint structures, it will attach a probe to it so that your callback is called whenever that function is called. So this is the output of Linux tracepoints against our VM where that proof of concept was active. You can see that the tracepoints for page free and page alloc were correctly found. The handlers were also correctly identified. The my module was the name of the proof of concept module that we created, and then you can see both of our probe functions were found as the ones that were handling the callback. Again, those are going to be called every time the particular function is called. We next looked at the K-probe interface. This also allows for hooking functions. You can specify the function to be hooked either as the name of the function or the address of where it is. For monitoring the function, you have 3 callbacks. You have the pre-handler, which runs before the first instruction. This is really the most useful one, especially if you're going to try to analyze rootkits or if you're writing a rootkit yourself, because this runs before the first instruction, which means that you can look at the call stack. You can also look at the parameters that were passed in and really gather everything that you need about that function call. The post handler runs after the first instruction runs. It's not at the end of the function. So it's a pretty special case. It's useful for debugging and things, but it really doesn't give a lot of value to malware. And then for the fault handler, this is where if that first instruction faults, your fault handler gets to run before the regular operating system takes over. Again, not extremely useful for malware, but it is available to code that's registering a K-probe. So as you can see in our proof of concept, we're looking for proc_sysopen. We call register K-probe with our filled out structure. And then this is what the output looks like in our new plugin. We correctly identified that proc_sysopen is the function being traced by the K-probe. And then in this case, we're looking at the pre-handler symbol, which is handler pre. The plugin does print the post and the fault handlers, but again, they're not very interesting in this example, and they made the output way too wide, so I cut them out. But if you're doing your investigation fully, you'll see all of those columns in the plugin output. The next thing we looked at was this Userland interface to K-probe. This goes through the tracing features that get exposed under sys when you have the kernel options enabled. In this case, we are creating a trace probe for the sysopen function. So there's a few things to look at here. One is you can see the name of our probe is testopen. The function being hooked is dosysopen, which is part of the control flow that'll be called anytime the open system call is made. And then we're telling it that we want the file name printed as a string. You'll see on the next slide how to figure out which parameters are available to which tracing events. But for this case, we want the file name, which is the file that's going to be opened. We then put that into the K-probe events file. On the next line, we enable our testopen event. And then after that, we're going to cat a file that doesn't exist. We just wanted a unique file name. And then if we grep part of that file name against the trace log, we see that we've captured our cat command. We see the name of the command is cat. There's then a dash with the 26136. That's the PID of the process. The name of this probe is testopen, like we said. The function is dosysopen, and then it's telling us the full path to the file name. So again, this is a really quick way to figure out every file that's being accessed on the machine, which program is accessing it, and so on. And then obviously with all the functions that are available to hook, there's really endless possibilities of what you want to monitor. To find all of the functions that are available as these event tracing handlers or ones you can hook, you'll want to look for format files under the directory. In this case, on this test VM, there was 1,529 of them. If you want to see which parameters are available for a particular function, then go to the directory for that function and then cat the format file. And then in this case, you can see we're looking for the sysenteropen system call. This is the first function that will be called in that chain that eventually ends up at dosysopen. And then you can see towards the bottom that it has a file name parameter. You also see that's a const_char, which is our const_char pointer, which is just a string in C. So you can treat it as a string, and then the kernel will figure it out for you and print it out correctly. But again, if you want to play with this yourself, figure out some interesting functions to trace, look at the format files so you can see what's available to you and what you want to log. This is the output of running Linux K-probes against the sample that had that command line trace event active. You can see that it correctly identifies the target symbol as dosysopen, but the pre-handler symbol is not so useful. It basically just tells us that it's this function in the kernel, and the function name is K-probe dispatcher. Obviously, there's no kernel module here. It was just registered from Userland, and the output needs to end up in that trace log file. So the kernel is going to handle that. So this helps us a little bit. We know that there is a trace event registered, but we don't actually know the name of it or anything like that. All we know is the function name. So if we want to get the rest of the information, we can run the Linux Trace Events plugin. This is a new plugin we developed specifically to handle those Userland trace events and being able to find them. We can see that our target symbol is the name of the probe, which is testopen, and then we get the format, which is the file name. You also see that the probe IP is being pulled and part of this format. That happened for every test probe that I set, so I assume it's just kind of there by default. But then after the probe IP, you can see what is the part of the format and the parameters that were actually set by the user. And then in this case, you can see it's the file name being treated as a string, as we would expect. So these plugins point to us right away that this Userland K-probe was set. The next thing we looked at was K-retprobes, and so this makes it where you can hook not only the beginning of a function, but also the end. And so this is really nice from a profiling standpoint, but also it's really nice from a rootkit standpoint, because by monitoring the end of the function, you can actually change the return value. So you can imagine if a rootkit wants to hide the presence of a file on a machine, it can hook the open functions that we saw before. If the file that's trying to be opened, the rootkit wants to hide it from the calling code, it can just change the return value at the end to say that the file's not there. The calling code will be none the wiser. It will have no idea that the rootkit changed that behavior, and it will just simply think the file isn't there. For our proof of concept, you can see on the right, we hooked the netlink send skb function. There's two functions of interest here, or two callbacks of interest here. As far as the K-retprobe itself, we have the handler member, which is going to be called when the function ends, and then the entry handler member, which will be called when the function begins. And so we want to track both of those with the plugin. And then you can see in the init function, once you have the data structure set up, you just call the register K-probe function, and then this will be active and that function will be hooked. Here's the output of running both K-probes and K-retprobes plugins against the sample. The K-probe plugins correctly figures out that the netlink send skb function is hooked, but again, it just essentially tells us it's a K-retprobe. So to get the full information, you need to run the Linux K-retprobes plugin. It tells us the function name as well as both the pre-handler and post-handler symbols, and also which module they come from. So at that point, you can just simply start your reverse engineering and you know the exact context that you're working. And then, as I mentioned, there is also the eBPF subsystem. This again allows programs to be compiled in user space, compiled down to that eBPF bytecode, and then ran by the kernel. And as I talked about, a bunch of companies and also systems rely on this. What you're looking at for our proof of concept is the source code to exec-snoop, like we saw before. And then we created a memory sample where a machine had exec-snoop running. And in this case, you can see that it reported that the cat command was used to read the password file. We can then use a couple plugins to examine this behavior. The first one is Linux eBPF. So this is going to list information on all of the running eBPF programs, or all of the active ones. You can see for this one, it is hooking the sysenter execve system call, and it's doing this by way of a Tracepoint. So we can then run the Tracepoint plugin, and we see that we have our hook set from the performance subsystem, and it's hooked on sysenter, which is going to hook the entire system call table, so any system call function in there. And then if we want to be able to map back an eBPF program to the process that actually loaded it, we then wrote another plugin, and that is the Linux perf events eBPF. It's going to match out these performance events filters, which is essentially what that previous program was, out to not only the eBPF program, but also the process that started it. So you can see here, if you look in the green squares, the address of the programs is the same, but in our perf events plugin output, we see that the program that's responsible for it, the actual running program that's responsible for it, is BPF Trace with PID 1109. So now we have the full context of this eBPF program that's running. In conclusion, hopefully you saw the value here of just how extremely powerful these tracing subsystems are, and the kernel infrastructure that provides them are, whether the malware is written as eBPF itself or something that hooks one of the lower subsystems. The entire system can be monitored, the full behavior of the system can be monitored, all through the use of eBPF. We were also very excited to see, and we realized that our research had some pretty good timing, that there's a talk at DEF CON and also another talk here at Black Hat about using eBPF for offensive purposes. So I put the titles to both of them. I would definitely recommend watching both of them. The abstracts sounded exactly like what our volatility plugins try to look for. The abstracts both talk about using eBPF to hook the system, to implement rootkits, and so on, which is exactly what our plugins are trying to detect. So these seem like really nice complementary talks. I'll definitely watch both of them as well. I'd also like to give a huge thanks to Gus. He's one of my co-workers at Velexity. He gave us a ton of feedback on the slides as well as a technical white paper, and he also wrote quite a few of the plugins that you saw here in the slides. If you have any questions or comments, please reach out to both myself and Golden. We have our email addresses, our Twitter handles, as well as our websites. Hopefully you enjoyed the talk. We will also be in person at the conference, so if you want to talk there, we can. Or like I said, just contact us anyway online. We're very easy to find.